Welcome to the Problems Channel Season 2, Episode 50, the episode which I titled A Diophantine Staircase, because in this episode we will solve a computer science problem that has an absolutely beautiful Diophantine setting geometric interpretation. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is to go to the homepage of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow the instructions that we give in that episode. If you have any questions, by all means, do ask them. When I will have time, I will answer them. But in that episode, we will explain and motivate everything that we do on this channel. In the computer science problem S2CS2, we are asked to use integer arithmetic only in order to find all the ordered pairs of whole non-negative numbers which satisfy the following strict inequality. The sum of squares of these numbers, let's say a squared plus b squared, must be strictly less than n, where n is a fixed and given ahead of time whole positive numbers such as 1, 2, 3, 4, 5, 6, 7, and so on. And here I have to apologize to my viewers because at the end of the previous episode, when I formulated this problem, I said that a zero intellectual voltage and a zero intellectual effort algorithm that just about anyone should be able to come up for this problem on the spot runs in the time complexity of big O of n squared. N squared, of course, I got too greedy and I got ahead of myself. Again, I'm sorry, I apologize. Evidently, the algorithm that everyone should be able to come up with right away that solves the problem at hand is big O of n, has the time complexity of big O of n, and we will discuss this algorithm in a second. But the actual challenge over here in this problem is to construct an algorithm that solves the given problem with the time complexity of big O of square root of n. Square root of n, big O of square root of n. And again, as another friendly reminder, in Season 1, Episode 2, we explain how to practice mathematics correctly. I usually do not give out these reminders. I think and I hope that all of our viewers are indoctrinated enough to do the right thing on their own. But here, just in case, wrapping up the second season on our channel, I want to remind you guys that if you were not able to solve this problem completely correctly and on your own, then we suggest that you do not watch our presentation in its entirety, but instead only watch the minimum viable amount of information that we will present. And as soon as you catch the whiff of where things are going, as soon as you realize that, this is how we can construct an algorithm that solves the problem at hand and has the time complexity of big O of square root of n, we recommend that you put the video on pause, walk away from the computer, and try to carry the solution of this problem completely on your own and to the end. That is done correctly again and on your own. As I declared in the banner of this channel, we will be solving the problems in mathematics, theoretical physics, and computer science on this channel. But so far, our viewers may say, Roman, you made all these wonderful announcements, but so far we have seen only you solving problems in mathematics. And the answer to that is yes. If we want to study theoretical physics and computer science, then in any properly structured curriculum, the program in mathematics has to run ahead of the majors for theoretical physics and computer science by evidently minimum of 1 semester, but this is not realistic. Ideally, we want to have at least 4 semesters of mathematics ahead of time, ahead of the curriculum in theoretical physics and computer science. That is because when we study mathematics and we study a way to solve problems in mathematics, we develop an overall skill of solving technical problems. And we can carry that experience from the context of mathematics into the context of theoretical physics and into the context of computer science as well. And here is no exception. And here's a perfect demonstration. In order to wrap our brain around the challenge, even in mathematics, we may sometimes, or maybe quite often, when we deal with a difficult problem, generate a brute force solution that is not too clever, that is not too elegant, that is not too beautiful. But when we generate such a solution, we also may comprehend the scope of the challenge. What is the challenge that we have to overcome? What is the problem that we have to address, the technical issue? So here in this problem, this is a computer science problem, and we see that just about every one of our viewers on this channel should be able to put this algorithm together. It takes pretty much zero intellectual voltage and zero intellectual effort to come up with this algorithm, but the idea of this algorithm is the following. Here I presented an implementation of that algorithm using the best programming language of all times, C. If you do not know C as a programming language, then do not worry about it. The syntax of the C programming language is very straightforward. It's self-descriptive. And again, if you have questions, then don't be shy. Use the comment section to ask your questions. I will put the entire text in a nice form into my GitHub repository as a free PDF file. I'll provide the link. You guys can download, play with it, or implement it in your favorite programming language. This is just an example. So the first several things over here are the idiosyncrasies of the C programming language. You don't have to worry about it. We do the inclusion of the so-called header file so we can have the prototypes for the function that executes the terminal IO, that's called printf, formatted output. And we also need another function. The standard IO is needed for the printf, and the standard lib, this header, is needed for this function a to y. Again, this is nothing that is required by the strict rules of computer science algorithm. We do not need that, but I want to put together a usable example, something that you can compile, run, and test, and play with, and start modifying right away. As such, the first two includes are the idiosyncrasies of the C programming language. The standard IO header file is needed for the printf function, and the standard lib is needed for the ASCII to integer a to I function over here, and we use this function in order to acquire from the command line the value of the bounding number that puts a bound on the sum of squares a of variables a and b. Extern int, main int, argc, char star, argv. Again, C, this is the C programming language idiosyncrasy for getting an entry into the executable image in your program. This is just a way to tell the compiler that this function will be external and it will return an integer. I will not get into the details of linkage specification. Basically, main is the name, and these two guys are the arguments. This is argc, is the count of the arguments, and this is the vector or an array that contains all the arguments. argv sub 0, the first one, will be the name of this program, and argv sub 1 will actually be the argument of that will become n. So the idea here is fundamentally forget about all the idiosyncrasies of the chosen programming language. This is completely separate from computer science. What is the essence of this big O of n algorithm? The essence of this big O of n algorithm is to vary the variables that will store the current values of A and B, these two guys, independently of each other in a construct known as a nested loop. For example, here we declare that the integers will be our usual suspects A and B. S, the variable S, will store the total amount of ordered pairs of numbers A and B such that the sum of their squares is strictly less than n. And A square and B square, these two variables, this one and this one, is again tiny optimization so that we don't have to compute the product of numbers with themselves more than once. Again, it's not that crucial, not that important. You guys can get away with it. You can just play with A times A less than n and B times B less than n. But the idea is to vary these two variables, A and B, independently of each other. And then once we saturate these variables with current values, run the test, which is what? Remember, we have to find the pairs of ordered pairs of whole non-negative numbers, A squared plus B squared, that is strictly less than n. So this is where we do it. In other words, we create 1, 2, 3, 4 variables, A and B, A squared, B squared, and S. Another variable, n, which is our upper bound over here, n. Then we initialize the total count, the output of the algorithm, to 0. And this is the overall structure of our big O of n. Big O of n, we will understand in a second where did it come from. In the outer loop, for example, we vary the values that are stored in the variable A. It is this guy right here. Now, we're asked to use integer arithmetic only. In other words, we're not allowed to use any mathematical libraries that are available in many programming languages. In the C programming languages, you will link the mathematical library with -LM command line options. This is a linker specification, the command line option that goes to the linker, but we're not allowed to do any of that. We just have to use the integer arithmetic. And how do we do that? Well, we will, instead of saying A less than square root of n, we will say A times A less than n and B times B less than n. Evidently, that is a reasonable upper bound for the square of A and the square of B, because remember, we're asked to find all whole non-negative that includes 0 numbers such that the sum of their squares is strictly less than n. So in the outer loop, we will vary the values of the variable A from 0 in such a way that A times A is less than n. In the inner loop, as we vary the values of the variable A, in the inner for loop, we will do the same thing to the other variable B. This is this guy. B here, B here. We initialize both of these values to 0. Why 0? Because the numbers A and B, the ordered pairs, have to be constructed from what? Non-negative, which means zeros including. Then we condition our for loop on the requirement that B times B or B squared is strictly less than n. We execute this operation, B times B. We store the value in the variable B squared. We do the same thing in the outer loop when we compute the square of A times A. We store it in the variable A squared. And then here I highlighted in red for you guys to see. This is the heart of the matter. This is where we test this inequality. So this test looks as follows. If A squared plus B squared is less than n, we increment the number that stores the total number of ordered pairs that satisfy this inequality by 1, S plus plus. You can also say, for example, another way to say it is what? Another way to say it is basically S equals S plus 1. This is the equivalent expression. So we increment S by 1 and we move on. Over here, after we increment or before, depending on how you like it, you can do another printf and print out the ordered paired AB. You will say printf, open paren, %d, comma, %d, close paren, \n for the new line, double quote, comma, space, A, comma, space, B, close paren, double quote. This is not too complicated. So what is the time complexity of this algorithm? Well, let's estimate it together. The outer loop runs for how many iterations? Well, we're using integer arithmetic only. We are honoring or we're fulfilling the demand of the problem statement. So the outer loop will run for the square root of n times, and for each one of these square root of n executions, we will execute the inner loop how many times? Also square root of n times. And for each such execution, we'll do the test. So this is where we pay the price over here. This is where we pay the price. This is our main operation, and how many times this operation will be executed. Well, square root of n times square root of n, and that is equal to what? That is precisely equal to n, and that is why the time complexity of this algorithm is big O of n. Again, zero intellectual effort in the algorithm, zero intellectual voltage, nothing interesting going on. The construct known as a nested loop. In the outer loop that runs in square root of n times, we run another for loop that also runs in square root of n times. We execute the main operation that addresses the heart of the matter at hand, checks this requirement, and if the check evaluates to true, if the test succeeds, then we increment the total count for the number of ordered paired of whole non-negative numbers that satisfy this inequality. Otherwise, we do not. We will move on, and at the end of this program, we basically print out to standard out the result, how many ordered pairs. Now, for those of you guys who still want to experiment with the C programming language, these days you can find all sorts of C compilers online. You will do the following. Let me use maybe green chalk to show you guys. You open up the terminal window and you type in the following: gcc minus g minus o, let's say square inequality dot c. This is basically the way for you guys to save this code in a disk file called sqn square inequality.c, and this is the instruction for the C compiler to compile this code into this output, into this executable image. Minus g will save the symbols in the executable image, so it's easier for you to debug. If you put this program in the debugger and step through the code in the debugger, minus g will make it very helpful for you, very straightforward. And minus o is basically says the output of your compilation should be blah, sqn. And how do you run this program? Dot slash in the terminal window sqn, give it a space over here and say, for example, 11. This 11 will be picked up by the operating system, pushed into argv sub 1. Here it will be converted, no error handling, everything is good, and then the program will run, and produce the output that you may expect. Now, this is the big O of n, zero intellectual effort, zero intellectual voltage in this algorithm. The challenge is to construct an algorithm that solves this problem at hand and runs in the time complexity of big O of square root of n. How can we do that? Again, you guys should think on your own, but as a hint for those who still did not solve this problem on their own and correctly, here is a hint. Sometimes naming the variables helps and will push the students in the right direction. What if instead of variables a and b, we will use the variables x and y, such that x squared plus y squared less than n. Does that ring a bell? Put this video on pause, think on your own, then try to generate a correct technical idea and compare that idea to ours. Here and now it should become evident why during the season 1 and season 2 we have studied all these problem-solving approaches in the context of mathematics, because these problem-solving approaches, as I promised during all this time, they travel far and wide, not only within all sorts of mathematical layers, but they travel far, well, and wide into theoretical physics and computer science. And here is a perfect example of how the problem-solving approach that we studied prior does just that, travels far, well and wide into the land of computer science from the land of mathematics. And which problem-solving approach would that be? Correct, that would be our actually second problem-solving approach that we have studied so far. Remember, early on in season 1 we studied the very beautiful and very powerful computer problem-solving approach known as transform and conquer. And the very second problem-solving approach that we studied right after transform and conquer was what? Was reinterpret and conquer. And according to the technical mandate of the reinterpret and conquer problem-solving approach, what should we do if we want to apply that approach to the process of generating a solution of a given technical problem? Well, if we want to apply the reinterpret and conquer problem-solving approach to the process of generating a solution of a given technical problem, we should carry out or come up with, invent, synthesize, discover, construct, pick your favorite verb that you think describes the situation, but we should invent a reinterpretation of the material, of the local material in the given problem that honors how many constraints? That honors two constraints. Those who studied the reinterpret and conquer problem solving approach with us should remember two constraints, which are what? The first constraint of the reinterpret and conquer problem solving approach is that our reinterpretation should do what? Should preserve the technical essence of the original problem. Exactly, because we do not want to solve some other problem. We want to solve this here given problem and no one else. So the first constraint that the reinterpretation that we're looking for in this case should be what? We have to preserve the technical essence of the given problem. And the second constraint of the reinterpret and conquer problem solving approach is what? The second constraint is that while we think of or invent or discover a different interpretation of the local material, that reinterpretation should provide us with a competitive advantage. Of course, because what is the point of reinterpreting the local material and gain nothing from it? Precisely, these two things are in a way transactional. They come in one package. Reinterpret and gain a competitive advantage. Now, in this case, as I hinted at in the previous segment, if we name our variables that store the values of whole non-negative numbers as x and y, then x squared plus y squared strictly less than n, and the usual continuous, let's say, topology in the Euclidean plane will represent what? Well, both in real and complex analysis, x squared plus y squared strictly less than n will represent an origin-centered disk, with the boundary of the disk removed or punctured out. But we're dealing with computer science. This is not usual continuous topology over real numbers. This is, in a way, Diophantine topology over integers, over whole numbers. And what does this Diophantine topology suggest? Well, in this case, a Diophantine topology under a fairly wide but technically accurate artistic license. A Diophantine topology could be what? Could be the nodes of a unit square lattice. Yes, we dealt with the unit square lattice a number of times in our mathematical adventures. Now the time to cash that check, so to speak, and gain the benefit from our work with the unit square lattice. Every node of that unit square lattice can be interpreted precisely as an ordered pair, x, y. You see, this is how these things work. That works under continuous topology over the set of real numbers. That works also over the, let's say, discrete or Diophantine topology over the unit square lattice, where each node has what? Has precisely integral coordinates x and y, where x and y are both integers. Now, in our case, because we are asked to find all the ordered pairs of whole non-negative numbers x and y such that x squared plus y squared is strictly less than n, a successful reinterpretation that honors both requirements that we just discussed is the following. What we're asked to apparently to count in this problem, not just the ordered or abstract ordered pairs of whole non-negative numbers, but we're asked to count the number of blue dots or the nodes of the unit square lattice with an appropriately chosen orthogonal coordinate system that are located where? That are located in the first quadrant, as shown on the right hand side of your screen, and strictly inside of the origin centered circle that has the radius of square root of n. I do not have much room over here, guys, but you understand that with all nitpicking rigor, what we have to write over here is that open paren, square root of n, comma, space 0, close paren. This is the full coordinate of this point over here on the x-axis. And over here we have to write what? 0 for the x component, open paren, 0, comma, space, square root of n, close paren. You all understand that. But this is the depiction or a successful reinterpretation of the given problem. The x-axis, the y-axis, the origin, this is 1 right here, this distance is 1, this distance is 1, scale with respect to or along both coordinate axes is 1 and the same, the origin is shown over here, the angle between the coordinate axes is what? Is precisely pi over 2 radians, is shown over here, origin centered circle of radius square root of n. Throw out the 3/4 of that circle, only grab the material that is left in the first quadrant, count, come up with an algorithm that counts the number of the blue dots that are located on the x coordinate axis, y coordinate axis, and strictly inside or under the bounding arc of the origin centered circle of the radius square root of n. Now, some of our viewers will say, Roman, what gives you any hope to think that the algorithm that is based on this reinterpretation of the problem will have a better time complexity than the time complexity of the big O of n algorithm that we looked at just in the previous segment? Well, the answer to that question is the following. What gives us hope to think that the algorithm that will be based on the new reinterpretation of this problem will be better in time complexity than the original algorithm that we just looked at is the following. Here, before I deep dive into the underlying mathematics, I would like to suggest that you guys try to come up with different stories as you develop a solution of problems, or maybe if you try to explain your solutions to others, try to come up with all sorts of stories that are funny and sometimes perhaps even ridiculous. But I suggest again that you are not that you do not be afraid of the fact that your stories will come across as ridiculous, but these funny stories should be not the exact painfully precise mathematics, but somewhat detached common life setting, but still a story that helps you understand the material in your solution or the idea of your solution, and that is the purpose of such a story. So here is one. Those of our viewers who watched the absolutely funny movie with Bill Murray and Rodney Dangerfield called Caddyshack, I remember this nasty gopher who kept digging tunnels under the golf course and popping up all the time, giving the groundskeeper in this golf course, Bill Murray, all sorts of trouble. So imagine that we're a clever gopher, or maybe a mole, who digs a tunnel along the x-axis over here, and every 1 unit of distance, this clever this clever mole or a clever golfer. Maybe that mole or golfer has a degree in computer science, you never know. So this mole or golfer comes up from underground and pops his or her head out. What is going on over here? 1, 2, 3, 4, 5. So once our clever golfer or mole keeps digging this tunnel and popping up every 1 unit of distance, how far will he or she be able to go? Well, he or she will be able to go as far as the bounding arc of the origin-centered circle of the radius square root of n, but that golfer cannot touch that graph of that circle. It has to stay strictly inside that circle and not touch the circle. So if we touch the circle, we back 1 unit up until we hit the closest integral point on the x-axis. That much should be understood. In other words, our golfer or mole can go as far as the largest but smallest than square root of n number on the x-axis. That much should be understood. Or if you do not like digging tunnels underground and going eastward, we can imagine that we are a dexterous monkey, let's say, or a rock climber, whatever your technical imagination allows you to come up with. That's what I mean when I say come up with all sorts of funny but technically accurate, perhaps maybe sometimes even ridiculous stories, but the stories that technically capture the technical essence. So if you're a rock climber or a dexterous monkey, you step into the origin point with the coordinate 0, 0, and you begin climbing. You begin climbing up the y-axis, and every 1 unit of distance, if you're a rock climber, bam, you put the nail in or whatever, nail it in, put the rope in there and keep climbing. If you're a monkey, maybe you pick a banana over here, make a mark on the trunk of the tree, throw the banana down, keep climbing. 2, 3, and so on. So how far will you be able to climb that way? Well, that way you will be able to climb again as high as possible until until you will bump into the graph of the bounding origin-centered circle of the radius square root of n. And because of the strict inequality, we have to come down to the highest, lowest integral point that is just under the arc of the bounding circle. That is how far we can climb up the y-axis over here. Now, what price in terms of time complexity will we pay for that climb, let's say? Well, it should be evident that in terms of time complexity, the price that we will pay for this climb over here will be what? Will be precisely square root of n. And by doing so, what will we do? So this is where the technical essence of our advantage that we will gain in the upcoming algorithm. Well, by climbing up, for example, the y-axis into the highest legal point, or the highest point that has an integral coordinate that sits just under the bounding arc of the origin-centered circle of radius. And we gain actually 2 advantages. We gain two benefits. First of all, we count how many blue points are on the y-axis that satisfy the requirement, the constraint of the given problem. X squared, x is 0, plus y squared is strictly less than n. Boom, we're here. We already counted all the blue points that sit on the y coordinate under the bounding arc. But by doing so, also think, what else did we do? Correct, by counting, by climbing up to the highest legal point, we also counted the number of blue dots under every column to our right. Think about it. The way the geometry of a circle works is that in his theory of circles, Euclid, that was book 3, Euclid's Elements book 3, when he develops the theory of circles, the tangent that runs to our circle through that point, square root of n, right? This tangent right here. This is one of propositions in Euclid's Elements in book 3. Euclid proves that between the tangent to the circle at this point and the circle itself, it is impossible to inscribe any other straight line that precisely touches this circle at that point. If you try to draw any straight line through this point that is not a tangent, you will necessarily intersect the circle at some other point. But here, the way things work is that our circle constantly runs away from that tangent, and that means all the other integral points, which are the nodes of a unit lattice or unit square lattice, they will be sitting precisely under that tangent. But that tangent, in a sense, what? That tangent represents the highest legal column that works for us. What is the definition of a legal column? A column is legal in this case if all of its blue points sit strictly under the arc of the bounding circle, origin center circle, or the radius square root of n. This is our legal column. So how does that translate into the actionable material? Well, we climb up the y-axis to the highest legal point, for example, and then by doing so, we will know we're strictly under the arc of the bounding circle. And then we step right, we step this way once. And then once we arrive at that point, first of all, remember, we know how many points are underneath that column. From this point, we know because we paid the price for it once, for that material, for that information once. We know how many points are underneath that column. And if that column is still legal, if we're still under the arc of the bounding circle, then we simply add to our total. We will say what? We will say S is equal to S sum total plus some amount of material, the y coordinate plus 1, the way these things work out. Don't worry about it. You will figure out what this expression is. But basically, that means that how many points are under that column. We add this guy. So if we're still under, if after stepping right once, we're still under the arc of the bounding circle, S equals to S plus that many points. So here, that many points go into the sum total. S plus equals number of points under this. But if we step right once over here, and this point turns out to be not under the arc of the bounding circle, what do? Well, in a way, we step back once and we step down. But because we step down, and here we will step right once, what did we do? Well, we just decremented the height of the column, but we still know how many points, how many blue points, how many nodes of the unit square lattice are underneath us. If we look down, we know, that many. It's just one less. And if we're at this point, for example, still not under the arc, we'll keep coming down the y coordinate by 1 until we are under the arc of the bounding circle. It's that simple, that's straightforward. So here we step right once, we test, are we under the arc of the bounding circle? Yes, we are. We know how many points are under that column. S plus equals that many points. Step right once. Are we still under the bounding arc? Yes, we are. We know how many points are here. S plus equals that many points. You see, computationally, zero effort needs to be done to add that many points. This is the beauty of this algorithm, and this is the beauty of this reinterpretation. By climbing up once, we locked in the knowledge for the height of each and every legal column. We do not need to do any more computations. We can just say S plus equals that many points underneath the current column on top of which we sit. That's it. So here we test, we're under, add, step right once. Are we under the bounding? Are we under the arc of the bounding circle? No, we are not. Step back once, and at this point, let me use the green chalk, guys. I hope you can see that you will not mix it up with the blue color. Here we step down, but the fact that we step down, we just decremented some variable in memory that will be very fast, and we still know how many points are underneath us. We step right once, we run the test. Are we under the bounding arc? Are we under the arc of the bounding circle? Yes, we are. If we shine a laser light, for example, or send a sonar, if you will, ping, ping. We know how many points, how many blue points are underneath us. So we add, let me use the white chalk over here. We add that many points. We know how many points are here because, again, we already paid the price for that knowledge on the way up once. That's it. After that, we just reap the benefits of that knowledge. And we added that many points to our sum total right here. Step right once. Are we still under the arc of the bounding circle? No, we're not. Back up once, go down here once, test, and then right. Are we under the arc of the bounding circle? Yes. Add that many points. We know how many points are here. We don't have to pay any computational price for that knowledge. We already know. We locked in that knowledge on the way up. And so on we go. This is not happening, not happening, not happening. So now you guys, that you understand what is going on, you tell me, what does this formation look like? Right, down, right, down, right, down, right, down. Let's say here we're out, again, down, right, and down, this way. What does it look like? To me, it looks like a staircase, right? We can walk that staircase upward against gravity, or we can walk that staircase downward with gravity. And because that staircase is built on what? On a discrete coordinate system, if you will. That is how I came up with the name, and that's the explanation for why I named this episode and big O of square root of n Diophantine staircase, because the staircase is based on the discrete topology, if you will, discrete coordinate system that is based on the nodes, of a unit square lattice, each of which has integral components. So now that we understand the essence of the competitive advantage that this geometric reinterpretation of the local material affords us, let us see how many choices we have for writing a different algorithm that implements this idea. If you understood the technical essence of why will we gain a competitive advantage by using the shown behind me geometric interpretation of the given problem, then you should understand that we will have two distinct ways to implement the algorithm that is based on this geometric reinterpretation. The first such implementation can be based on the idea of what? The first such an implementation can be based on the idea of us walking along the x-axis first into the farthest legal point on the x-axis, or technically the point that has which coordinate? X max, which is, or the highest value of max that is still under, this is my improvisation over here, the less than in the circle, saying that the largest value of x that is still less than square root of n. This is a point over here on the x-axis. It has integral coordinate 0 and the largest value of x such that that x is less than square root of n. In that case, we will do what? In this case, we will climb the Diophantine staircase up, and we will do work in terms of physics against gravity. By doing so, we will approach what? We will approach the point on the y-axis, that has which coordinates? 0 for the x component over here, and y, as we explained in the previous segment, largest value of y, still less than square root of n. Again, this is my improvisation. I do not want to invent any more symbolization as we have to, but you guys understand what's going on. So in this case, we will do what? In this case, we will be decrementing x. We will be decrementing x for as long as what? What's the bounding condition will be? Well, in this case, the bounding condition will be x is greater than or equal to 0. This is our loop when we step left. And in this case, what will be the terminology? Well, instead of heights of columns, it will be widths of rows. it should be understood that this is the beauty, this is where again we reap a benefit of this wonderful geometric object to which we refer as a circle. The distance along the axis x over here, or the points at which our origin-centered circle intersects our coordinate axis, will be the same in both cases. In plain English, this distance over here, bam, and this distance is the same here to here, here to here. So that is the first implementation of the algorithm based on the initial horizontal motion. But the second implementation of the algorithm that is based on the idea is based on what? On the vertical motion. First, we climb up the y-axis into the point that has coordinates 0 and y max still less than square root of n, this point of over here, and then we do what? We do x plus plus, but then y minus minus, until that is y is, in this case, will be y is greater than 0, and in this case, we will be climbing into, we will be doing work with gravity, will be slithering down this Diophantine staircase into which point? Into the point that has these coordinates over here, and this will be our bounding condition for the descent. So once we understand that, for demonstration purposes, I will show you guys an algorithm that is based on the initial vertical climb, but just for fun, I suggest that you try to implement this algorithm based on the initial horizontal motion. Again, behind me, you see an implementation of the algorithm that we just discussed that is based on the initial vertical motion up as far as possible, as far as legally allowed along the y-axis in the best programming language of all times. See, I will not be showing all the details, and again, do not worry. The links to all the free PDF files where I have all the code that you can download and play with at your own time, at your own volition, are in the comment section. Dig through the comments, find the files, click download, do the needful. But the idea here is the following: I only show the technical lessons. All this pound includes standard IO, pound includes standard lib, extern, int, main, argc, argv, papa, int, this, that. None of that is here. We do not need that. Just the essence, and that essence is quite simple. Again, remember my references to the fact that mathematics is an art form, and a beautiful mathematical idea is virtually indistinguishable from a beautiful painting or a beautiful sculpture, for example. Here again, a beautiful idea leads to beautiful code. The code is minimal, it's very straightforward, but it gives us competitive advantage and generates a better time complexity than the previous algorithm. In other words, based on the idea of climbing initially up the y-axis into the highest point, as we discussed in the previous segment, here is the code. First, I show in red on top over here, the loop is straightforward while y.y is strictly less than n. This is again the requirement to use integer arithmetic only, no math libraries of any kind. We do y++. Again, if you are not familiar with that syntax basically means, in terms of simpler expression, it will be y equals y plus 1. Increment the value of y by 1. What does this code do? Can you show me the code that is shown over here in our geometric interpretation? Well, that piece of code is exactly that part, climbing up into this point. Now we climbed into that point. Look at this code. While y is greater than 0 is the condition on this while loop, which means what? Which means that we want to stay within the first quadrant. We do not fall through into the fourth quadrant. We want to stay in the first quadrant. This is the condition that ensures that we stop over here. We do not step below. And overall, again, this is another miniature quiz for you guys. What is going on over here? What's going on over here is that I maintain the following invariant that consists of two pieces. At any point through our algorithm and in our loops, the point xy sits on the top of the highest legal column, here, 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 these guys. That's number one. Number two, the variable S over here, the variable S, stores the sum total of all the number of all the blue points that whose columns we have visited so far. So this is the invariant in our cycling, in our looping code. So for as long as y is greater than or equal to 0, this is the outer loop. That outer loop ensures that we stay strictly within the first quadrant, and we do not fall through to the fourth quadrant. What do? Well, this line right here that I show in yellow, this line over here, corresponds to what? Can you show me the geometry of this line of code? S plus equals y plus 1. Well, basically, this is a shorthand notation to write S equals to S plus y plus 1. Well, this is adding all the number of the blue points that are directly underneath, under our stair that we sit on right now. S equals to S plus y plus 1. This is the sum of all the blue points that we're sitting on top of which right now. The next line, x plus plus, which is the same as saying, let me write it in parentheses, x equals x plus 1. What does this line do? Well, this line does this. One step rightward. We step east once because this is our discrete topology. We cannot be stuck somewhere here, here, here in the middle. It has to be one step because this is the smallest unit which increments or decrements an integer. X equal to x plus 1, step over here. So this is the geometry of this line of code. And now what do? Well, this little block of code, this is pretty much it. It says while y is greater than or equal to 0, and this is our condition, x squared plus y squared is greater than n. What do? Y minus minus. This block over here, also very straightforward. It is, what is the purpose of this code? Can you show me the geometry of this code? Well, the geometry of this code is this one. If we step outside, we keep going down. If it so happened that, for example, we hit couple points, this point, then we skip down this way, skip down this way. This is the while. Ensures that we keep slithering down for as long as we are above the arc of the bounding circle. And what? Y is greater than equal to 0 ensures that we're still in the first quadrant. That is why we need this condition over here. Y minus minus, again, for those who are not familiar with the syntax, it is basically saying is y equal to y minus 1. Decrement the current value of y by 1, and that is the motion over here, the downward motion. So the combination of this code and this code is precisely the artistic equivalent of our Diophantine staircase, and the fact that x goes plus plus and y goes minus minus, we increment x by 1 and y by 1 also. That means that we are slithering down the Diophantine staircase. And this is pretty much it. This is all there is to it. Now, why is the time complexity of this algorithm is big O of square root of n? Why is that? Well, this here line of code, our climbing, we already know this is square root of n. That much we know. But unlike the first algorithm where we had a nested loop, and for each of square root of n iterations, we had another square root of n iterations, which produce the product of square root of n's. Here, what is the duration of this loop? Well, this loop over here, and combined with this condition over here, is what essentially? This is another square root of n. We will descend square root of n steps down, and we will venture right along the horizontal direction, also not more than square root of n. This is another square root of n, but this time the square roots of n's are added, square root of n plus square root of n, so for a total of a square root of n. So in this case, what we have done is we essentially decoupled our monolithic structure of the nested for loop that we had in our first zero intellectual voltage, zero intellectual effort algorithm. And if we were to show this algorithm to someone else, if we were to hide our geometric interpretation, and to a person who has no idea what is going on, we just show this here code. Initially, this code will be somewhat bewildering. I guess maybe the smarter cucumbers in the audience will eventually figure out, oh, I see what's going on. X, Y, origin centered circle, nodes of the unit square lattice. I see what's going on. This is, now it's clear. But initially, without the interpretation, and we keep the viewers in the dark about our geometric interpretation, that code may be bewildering and may not be that obvious, even though it is correct and it gives us an algorithm whose time complexity is precisely big O of square root of n, and we're almost done. If the impatient kind in our audience can skip the next couple segments and move on to the next challenge. But for the curious travelers, I will suggest another short quiz. Do you guys think this algorithm can be improved some more? Think about it, put this video on pause, generate your idea, compare your idea to ours. But my hint to you guys is look at what is going on with our quarter circle and think which geometric object will give us the impetus for yet another. In the big scope of things, yes, it's a childish improvisation, but as a, let us say, slow and not so loud, but still a standing ovation to the abilities of the human abstract cognition, because we, the humans, can. We squeeze this geometry over here, the geometry of our successful reinterpretation, some more, and cut the running time of this algorithm by how much? Well, that is another hint, by 2. In the big scope of things, yes, from the raw computer science perspective of the big O notation, this is nothing to write home about. We're just fighting for the factor, for the constant multiplicative factor over here in front of the square root of n. We're not improving our time complexity of our algorithm drastically. We're not making it log of square root of n or n raised to the power 1/5 or 1/10. This is just a childish, in some sense, optimization, but still as a very modest and quiet, still standing ovation to the ability of the human mind to think abstractly, because we, the humans, can analyze the given problem and squeeze that analysis for all its worth, for all its technical worth. Here, I suggest that you guys construct the bisector of the first and the third quadrants of our chosen orthogonal coordinate system and observe what? Well, what's going on here is one of your and my favorite words in mathematics, theoretical physics, and computer science, and that is symmetry. The mega experiment of studying the nature and the structure of symmetry is the theory of groups in mathematics. You should study it at some point. Maybe you can begin with my book that I put together free of charge, available on the internet at any time. Group theory for all, an elementary introduction to the theory of groups. But anyway, so let's say we construct our angular bisector of the first and the third quadrant of the chosen coordinate system. What can we say? Well, once you look at this picture, you should be able to say the following words. It is possible now to partition all the blue points, which represent what? We have a bijection between the blue points as mathematical objects and all the ordered pairs of whole non-negative numbers, such that x squared plus y squared is less than n. All these points can be partitioned into what? Into 3 different sets. One such set will be what? One such set will be all the blue points. I will now commit a little crime and use the blue chalk, guys, to engulf or include all these points over here, which run this way, this way, this way, this way, and this way. So I'll probably, let me just cross hatch it a little bit. So these points, all the blue points that are the solution of our problem, that sit logically above the set diagonal. The second set of such points will be what? symmetrical set of points that sits technically under that diagonal. So that will be this set of points. This, then it will go this way, this way, this way, this way, and this way. And it will go this way. So let's cross hatch it this way. This will be all the blue points that are located technically under the diagonal. And what is the third set? The third set are the points that are, or the points that form that diagonal. It will be, let me use for distinction yellow. It will be this point, this point, this point, this point, and this point. Somewhere here will be this point here, but it will not, we will not be interested in that point. Why? We will not be interested in that point because it lies strictly outside. It lies outside the arc of the bounding circle. And now, what is the root of this optimization? Well, the root of this optimization, it is enough for us to count only the number of blue points in one of these sets. Again, the one that's located below the angular bisector, the yellow angular bisector over here, or the ones that are located above the angular bisector. And by knowing these points, we can do very simple arithmetic. And at certain point, again, this is a miniature quiz for you guys. I'll answer that question in a few seconds in the next segment. But for you, the food for thought is the following. When will our optimized algorithm terminate in this case? What will be the condition for the termination of this optimized algorithm? If for a moment we go back to our original algorithm over here, at the end of the yellow loop shown over here, at the end of this loop over here below, what will be the output of our algorithm? Well, that will be the number s. Over here we will have a line which says essentially printf $d \n and then s for the value of the sum, because that number will contain the total number of all the blue points that are located in the first quadrant and under the arc of the bounding circle. That is the number that we were looking for. And in our optimized, in a childish way still, but a slightly optimized algorithm, we want to count what? We'll still use the variable s for the number of blue points, but this time we will designate with s in the value of s, in the variable s, we will keep the number of blue points that are located, let's say, strictly above the angular bisector shown here in yellow, or as we can say, a diagonal, because it is in a way a diagonal of the corresponding square. So now if we have that number, if we compute that number, then what can we say about the output that we should produce over here? Well, instead of s, there should be some sort of arithmetic form of an arithmetic expression. And what that expression should be? Well, it's not that difficult to realize that the number that we're looking for must be what? That number must be 2 times s plus d. And what is d? So the output of our algorithm, this is the output. This is what we're looking for. D is the number of what? D is the number of points on the diagonal of our formation that is located where? Still under the or inside of the origin center bounding circle. How many numbers, for example, here? 1, 2, 3, 4, 5. In this case, D will be equal to 5. Whatever S comes out to be, we multiply by 2 at the number of diagonal points. And voila, we can short circuit our execution and do not traverse the entire first quadrant, but hop off that slithering process along the Diophantine staircase, parabolically speaking, halfway through that staircase. So what is the condition for the termination of the algorithm? Well, in plain English, the condition is the following. The moment we jump on the highest legal diagonal point, bam, game over. We jump off, the algorithm terminates. But what does it mean tactically in terms of actionable computer science? Well, the actionable computer science, again, is quite straightforward and, again, beautiful. It all comes down to how beautiful things produce beautiful things. When x is equal to y, see, this is the condition. When x is equal to y, this is the termination point. Beautiful, absolutely awesome. Why is that? Well, remember, we maintain through our while loop the following invariant. The point with the coordinates xy, the point with the coordinates xy is the point that sits on the very top, the highest point of the legal column. And s, well, in the old algorithm, that used to be the number of all the blue points that from all the columns that we have visited so far. Here it will also kind of preserve its meaning, but again, we will only count the points that are located above the diagonal. We'll show how it's done, and notice that why this plus d over here must be present. Well, because the number of diagonal points over here will be equal to what? Well, it will be equal to the height of the corresponding column. Once we detect that x is equal to y, or y equal to x, game over. Every point corresponds to the corresponding here, and voila, the number of diagonal points is still the height of that column, and the game is over. And this is what the code will, for that algorithm, will look like. Again, do not worry about the details that you see on my board. All the code is available in the free PDF file. The link into that file you can find in the comment section. I organized all the code that you will see and you saw in this episode in one convenient place. You can play with it, download, but here I'll only show the difference, what will be different in this optimization. The climbing code all the way up is the same. You saw the while y times y is strictly less than n, y plus plus code is the same, the code will be there. So here we run another loop that is greater than or equal to 0. That did not change also, but here we introduce an extra variable d. This guy, the variable d, integer d, will keep track of the number of these diagonal points over here. We increment the diagonal point every time we step. We increment the diagonal point. We step up this diagonal, that is y plus plus. The variable s stores the number of all the blue points that sit above this diagonal. That is done over here, and it is balanced with the minus equal d, so which is basically saying s equal to s minus d to balance things out, because we want to subtract these points below. We only count the points above. X plus plus is the same. We step right once by one column, and then the while loop that you saw before, exactly the same. Y is greater or equal to 0 plus x times x plus times y is greater than n. We want to still make sure that we are strictly under the arc of the bounding origin center circle of the radius square root of n. The code is the same. The only difference over here is you see that if we detect that we sit on the diagonal, we balance things out. We subtract 1 from x, we subtract 1 from d. Once you analyze the code, you will see why we have to do it. And then again, we reduced y by 1 because we step down and outside that loop. This is the condition over here that you guys see. If y is equal to x, d plus plus, and break. You probably cannot see that see it too well, but don't worry about it. Again, all the code is in the free file. Break over here, and this break takes us out of the outer while loop. If we detect that we are on the highest diagonal, we do a break. This is the end of this loop. And over here, again, in the code, you will see that there will be a printf. The printf will say double quote, %, d, new line, what will be 2 times s plus d. This is the output of this algorithm, of the improved algorithm, %, d, \n, new line, 2 times s plus d. And the S is taken from here, the D is taken from here. Game over. Again, this will be technically 1/2 of the compared to the previous implementation that we show. It will still be, of course, big O of square root of n, but it's a tiny optimization that does not affect our time complexity materially, but still, again, as an opportunity to analyze and optimize things, this is what it is. And this is almost it for this problem, S2CS2. In the next short segment, we will consider what we guys suggest that you do after you solve each and every problem in mathematics, theoretical physics, and computer science, and that is generalize a given problem. One more time, in season 1, episode 2, we explained one way how to practice mathematics correctly, and our suggestion that every time you solve a problem in mathematics, theoretical physics, or computer science, you step back, inhale the experience of solving the problem, and try to abstract your solution and generalize your solution. This is two different things, very tall order usually, but here as a generalization, as a potential generalization, we can say, okay, in the original problem, we dealt with the pair, with an ordered pair of whole non-negative numbers. So one way to generalize is to extend the size of the foo-plet in our case. So in other words, instead of dealing with the pair, we deal with the triplet of whole non-negative numbers, ordered whole non-negative numbers A, B, C, such that their sum is the sum of their squares is strictly less than n is a fixed, given ahead of time, whole positive number, 1, 2, 3, 4, 5, 6, 7, and so on. The triplet, the order sensitive triplet over here is A, B, C, and the numbers are such that these numbers can be 0, 1, 2, 3, any one independently of each other. What is the algorithm to output the number of such all ordered triplets? We already know, again, the brute force implementation will be to vary 3 variables independently, construct a nested loop for A equals 0, for B equals 0, for C equals 0, square root of n times square root of n times square root of n. We already know the brute force algorithm, but we also know one potential implementation. If we grab a sphere of radius n, make that sphere to be origin centered in the corresponding, again, Diophantine topology, but this time all with the free space. Instead of taking a unit square lattice, we will take a unit cube lattice, all the cubical points in space that have their vertices as integral points captured in ABC, and then by the looks of it, what? 1/2, 1/4, 1/8. If we grab 1/8 of a sphere, here's my feeble attempt to show this 1/8 of a sphere. We already know how to deal with the two-space case, how to count all the number of blue points inside of a square, origin-centered bounding square. But now we need to do the same, but in more general fashion. And in this case, we need to count the number of such points in the xy plane and then step up this way and count the number of such blue points that are trapped strictly inside of an origin-centered sphere of radius square root of n. And over here, there will be another opportunity for optimization, that if we cut our sphere 1/8 of a square by the looks of it, with planes that are parallel to the x or y plane over here. This is y, this is 1, this is 1. What will happen? Well, what will happen is that we will get an sort of sibling image of what we have in the xy plane, but this time what will happen, guys? Come on, think on your feet. What will be going on as we do that with this sort of level lines? Well, the radius of the bounding circle will what? It will decrease, because at this level the arc will be shorter, at this level it will be shorter, at this level. So every time the size of the circle that is similar to one that we have in the xy plane will diminish a little. So maybe we can exercise that and also include it into our optimization. Maybe we will be able, maybe we will not be able. But again, the idea over here is that we can try to optimize our brute force algorithm by counting the number of blue points that are trapped inside the origin centered sphere, the number of blue dots, or the number of nodes of the unit cube lattice that are trapped inside of the origin centered sphere of radius square root of n. Now this is it for the problem, for the computer science problem S2CS2, and we will move on to a new challenge next. In order to celebrate the end of the second season on our channel, we will solve our first physics problem. Finally, it will be the problem S2P1. Remember that with the letter P, we designate problems in physics. So this will be our first problem in physics S2P1, in a way that is exactly, again, when people ask me why does it take so much time to solve the problem in physics or computer science, the answer is the same. In any properly structured curriculum for majors in physics and computer science, the corresponding math problem has to run ahead by quite a good and healthy margin. As such, in our first physics problem, where the question is the following: what is easier to tip over, a uniformly dense cube with the side length of a uniformly dense cube with the side length of A, or a right circular cylinder that has the height of A, the same height as the length of the cube side A, and has the same mass and the same density. Mass and density for these two objects is the same. So what is easier to tip over? This is a solid cube that is made from some material. The density of this material is rho over cube. We know what the volume is. We know how density, mass, and volume are connected. The mass of the cube is equal to the mass of the cylinder, and the density of the cube is equal to the density of the cylinder. Density of the cube is density of the cylinder. Rho is traditionally, at least in my time, rho was the letter for the density of certain substance. So here we're told that we have two geometric shapes that are made from the same material. They have the same height. One is a cube with the side length A. The other one is a right circular cylinder with the height A. The radius of the base and the top, you guys should be able to deduce on your own. You can compute correctly what is the radius of this circle given these two units of information. And the question is, which one of these shapes, under all other conditions in the near Earth gravity, everything is pretty much static, what is easier to tip over? And you need to justify your answer with a solid proof. Yes, this is physics, but what you will be generating is a proof. In this case, this will be proof in physics all day long. This episode in which I will share my solution of this problem will be informative, will be very informative, very useful, very interesting. I suggest you do not miss that episode. In just that one episode alone, we will learn a lot. We will learn a lot. We will basically learn the fundamentals of how physics works. And again, this material is quite simple. This is baby physics. This is nothing beyond middle school physics. And unfortunately, still, most students cannot solve even this problem, but we will use that problem in order to begin our study of physics. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the physics problem S2P1.